Hello, this is Ron Wade, Principal Systems Engineer in the Timing Division at Renesas Electronics, back with another part in our PCI Express reference clock jitter series. This section is part 2A, which is the SerDes physical layer building blocks and jitter transfer functions for the PLLs. The SerDes building blocks consist of a transmitter and a receiver, and SerDes is an abbreviation for serializer deserializer. So the transmitter brings in parallel data from the digital logic, serializes it, encodes it, and then sends it out the transmit serial port. And then the receiver does the opposite. It brings in the serial data from the receive port. It recovers the clock from the data and also the phase information from the data, and recovers the bits, which then get run through a serial to parallel converter, and you end up with back in your digital logic. So looking at these two diagrams, there's three major pieces. There's the TX and RX PLLs, and then there's the clock and data recovery unit. With clock and data recovery, there's two main types of that as well. One is analog, which recovers frequency and phase information. The other is digital, sometimes called a phase interpolator, that recovers mainly phase information. And this is the one we'll focus on throughout the rest of this presentation series. So a simplified block diagram of a PLL has three parts to it. There's the phase detector, which is looking at the input reference clock and the feedback and trying to align those both in phase and in frequency. There's a low pass filter, which is used to filter out high frequency noise, which tends to be present at the output of the phase detector. And then there's the VCO, which is basically responding to this control input and converting a voltage into a frequency. And the low pass filter is generally what is used referenced when specifying quote PLL bandwidth. And in first order PLLs, that bandwidth is usually the 3 dB point. And then in second order PLLs, specifying this cutoff frequency here is actually referencing the minus 6 dB point in the transfer function of the PLL. So the feedback, the VCO is fed back in here, and again, the whole system tries to make these two things identical in phase and frequency. You can put a divider in here, which is what most PLLs actually do. And if you say this ref clock's 100 and the divider is divide by 50, then this will end up running at 5 gigahertz. So the 5 gigahertz divided by 50 equals 100 meg, which equals the ref clock. So that's just a note for your information. We won't need that going forward. So we will need to understand what is a jitter transfer function, though. A jitter transfer function is a behavioral model, which means it's a mathematical representation, and it's used to describe how jitter is transferred through a system, particularly high-speed serial interfaces like PCI Express. In its simplest form, the transfer function is basically the transfer function of x is basically out x over in x, where in our case the input would be the reference clock phase jitter. So before we can make use of this, we actually now need to look at the jitter transfer functions of the various SerDes building blocks before we create an overall system transfer function. So the simplified PLL transfer function goes as follows. We have some input voltage, and we have an amplitude and sine of omega n at time t plus phase in of time t. And then the output is similar, except it's the output voltage or the output function is an amplitude times the sine of omega out t plus the phase out t, where the phase out and the phase in are absolute phase in time of the signal, of the input and output signals. If we were to take V out over V in, we would end up simplifying all this down, and assuming the amplitudes are the same and the frequencies are the same, we will end up with a phase difference here of phase out in time over phase in time. And this is a phase transfer function. So if we go to the S domain, we can write that as H of S is phase out of S over phase in of S. We can rearrange this and end up with this form of the function. And basically, as long as we know any two of these three, we can calculate the third. So PCI Express uses a second order low pass filter as the behavioral model for the PLL. And the key aspects of second order low pass filters are that the frequency roll off is minus 40 dB per decade, and the natural frequency of the filter is actually the minus 6 dB roll off point. So the S domain transfer function for a second order PLL is modeled as H1 of S and H2 of S. This is for the TX PLL and the RX PLL. And the only difference between these two formulas are the constants. The damping factor is zeta. So for H1, we would have damping factor 1, and the natural frequency is omega n, and we would have omega n1. And we would have likewise for H2 of S. So this allows for differences between the transmit and the receive PLLs. So what do these look like when we plot them? Well, they look like this. The blue is representative of the bottom line of these values lifted from the PCIe base specification, and the green are representative of the top line. So this is a 350 kilohertz bandwidth, the green lines, and the blue lines are the 700 kilohertz bandwidth. And you can see they actually cross the minus 6 dB point at those two frequencies. The other thing we can see here is for each decade of horizontal axis, which is frequency, we have minus 40 dB of attenuation. Again, the vertical axis was in dBc, the horizontal axis was in hertz, with this being 10 to the 6th or 1 megahertz, this being 10 to the 3rd or 1 kilohertz, and then 10 to the 9th up here for 1 gigahertz. So these are the parameters specified in the PCI SIG system, and that's what the PLL transfer functions for Gen 7 look like. So I'd like to thank you for joining me for this presentation, and the next up we will talk about the CDRs. Take care.